We've seen that mappings between objects in a category are called morphisms, and that mappings between categories, where we map both the objects and the morphisms, are called functors. So we might now ask ourselves what it would mean to map between functors. A mapping between functors is called a natural transformation, and is defined in the following way. Suppose we have two functors, one called G and one called H, both going from a category C to a category D. And suppose we take any morphism F in the category C, going from object A to object B. Well, then we know that the functor G will map F to G of F, going from object G of A to G of B in the category D. And we know that H will map F to H of F, going from object H of A to object H of B in D. And suppose that for every object, we can associate a morphism in D, going from the image of that object under G to the image of that object under H. For each one, we might call it lambda A, lambda B, and so on. This would mean that we are mapping between the images of the functors. And so a mapping between functors is not a single morphism, but rather a collection of morphisms, one for each object in the category, which we call the component of the natural transformation for that object. Now, of course, this is category theory, so everything is all about composability. And so what we'd like is that following this chain to get from G of A to H of B would be the same as following this chain, going from G of A to H of B. This property is called commutativity. And so a natural transformation is a collection of morphisms in the category D, one for each object in the category C, where the following property always holds. Lambda after B, lambda of B after G of F is equal to H of F after lambda A. So we can see that lambda B after G of F following this chain is the same as H of F after lambda A, which is following this chain. Thus, presenting the official definition, if G and H are functors from a category C to a category D, then lambda is called a natural transformation from G to H if lambda is a collection of morphisms in D such that there is one for each object of C, which we call the component of X lambda X. And if for any morphism going from A to B in C, we have the commutativity of the square that we just showed. Now that commutativity property is going to look different, obviously, whether we have a covariant functor or a contravariant functor. So in the covariant case, the commutativity property is exactly what we just saw. Lambda B after G of F equals H of F after lambda A. However, in the contravariant case, G of F is going to land us in G of A, so we would instead need to apply the component of A after. So we would have instead lambda of A after G of F equals H of F after lambda of B in the contravariant case. If it's the case that every single component is an isomorphism, that is, lambda x is an isomorphism for every x for every object in C, then we instead call this a natural isomorphism, and we write that G is naturally isomorphic to H. Supposing we have a natural isomorphism from a functor G to a functor H, represented in the diagram above, then we know first of all that every object X has a component lambda X which is an isomorphism, but that also means that every component has an inverse, a unique inverse, going back the other way in this diagram. So for each component, lambda A will have lambda A inverse, and lambda B will have lambda B inverse, and that this square commutes, since it's a natural transformation as well. This means that we can apply inverse lambda A on the right in both cases. These will cancel to 1 GA, and we'll get that H of F is equal to lambda for B after G of F after lambda for A inverse. But then we can look at the commutativity of the square going the other way. So what if we wanted to say that lambda B for B inverse after H of F, that is this chain here, lambda for B after H of F, is equal to G of F after lambda for A inverse, this chain here. So the commutativity of the square going the other way. Well, here we can replace H of F with this expression here. And then these two will cancel out to 1 G of B, which will leave us with just G of F after lambda of A inverse. But this is exactly the commutativity property that we were looking for. Lambda B inverse after H of F is equal to G of F after lambda A inverse. And so we get that any time that we have a natural isomorphism going from G to H, we also have a natural isomorphism going from H to G, which consists of all of the inverses of all of the components. Which all exist because they're all isomorphisms. Let's conclude by showing that the composition of natural transformations is also a natural transformation. So first we need to decide what it means to compose natural transformations. So suppose we have three functors, G, H, and F, and two natural transformations, one going from G to H called lambda, and one going from H to F called tau. We want to show that by composing the components for each object of lambda and tau respectively, we can actually make this big outside square commute, which will give us a natural transformation straight from G to F. So what we need to show is that tau for B after lambda for B after G of F is equal to F of F after tau of A after lambda for A. We need to show that g of f and then lambda of b and then tau of b, which is here, is the same as lambda of a, tau of a, and then f of f, which is here. But tau of b after lambda of b after g of f is actually equal to tau of b after h of f after lambda a. And we know this because we can apply the first natural transformation. Lambda b after g of f is the same as h of f after lambda a, which is here. But then we can apply the second natural transformation to this first part, because lambda of b after h of f is the same as f of f after tau of a, which is f of f after tau of a after lambda of a. But that's what we needed to show. Tau of b after lambda of b after g of f is equal to f of f after tau of a after lambda of a. So we see that the composition is in fact a natural transformation where the component for each object is just the component-wise composition of lambda and tau. Note that throughout this video, we have focused almost exclusively on the covariant functor version of the natural transformation without explicitly stating so. One exercise would be to watch through this video again and to reprove each result using the contravariant functor version of the natural transformation. The graphic for the contravariant version is up here, where we see that a morphism f from A to B gets mapped to a morphism g of f from g of b to g of a. We flip the order of the arrow. And same for the functor h, where the components will now be the opposite, and therefore the commutativity property will look like this instead.